Thank you very much. It's my pleasure to be here today. And my first slide is not about the stroke, it's about an advertisement, because I've been spending 2 years in the US, and every good movie and every good show on the TV always starts with an advertisement. So we've been lucky at Leuven, and thanks to the generosity of our university, we managed to obtain a fundamental research project to redo or to upgrade our understanding of the wind of massive stars, both the hot stars and on the cool stars, the red supergiant stars, both from the observational point of view and the theoretical point of view. So this is a little bit interdisciplinary project with Lenderson, Johnson Quist, and Alex de Cotter. And we're actually hiring, so if there's anyone interested, we have 2 PhDs and 1 postdoc, and the deadline to apply is the end of next week. So please forward this advertisement to anyone you think would be interested to work on single star. All right, so this crowd is a little bit different because you're already convinced that multiplicity is high among massive stars and that binarity is has important consequences for the evolution of stars. And this is 2 of the recent overview paper that shows that at a high mass, the multiplicity fraction is reaching close to unity. And what the organizer have asked me to do today is to provide you a little bit more insight into the observational campaign that have allowed to derive that kind of diagram for the massive stars. All right. So the first things I want to do is to clarify what I am calling a massive stars, because everyone seems to have its own definition of what's massive and what's less massive. So I'm focusing on the stuff that makes supernovae. And that for single star would be around 8 solar mass. If you consider binary interaction and mass gainers, it could be a little bit lower, but I would start with a minimum mass of 8 solar mass, and then I will make 2 differences between the B stars and the O stars. There's no good physical reason to make that differences, but observers tend to focus the sample either on the B star sample or on the O star sample, because the diagnostic lines are different. So the B stars would be between 8 and 16 solar mass, and the O stars would be about 16 to maybe 60, 70 solar mass, and at higher mass, I would say that the multiplicity constraints are really, really poor. Okay, so you all know this is the canonical evolution of a massive star, right? So, but if you want, there's a lot of different physics and different type of interaction that may happen, and what we as observer are trying to do is to provide you what are the multiplicity properties on the mean sequence, so that you can test the outcome of the formation models for massive stars, and you can also try to use that as input properties for different simulations to try to see what are the different fractions of evolutionary channel. So as an observer, what we try to do, okay, so there's one thing missing, okay. So we want to provide the multiplicity properties, and that is the multiplicity properties as a function of masses. So for the O stars, for the B stars, for the Wolf-Rayet maybe, for the higher 100 solar mass stars. We want to do that as a function of different age, because you can follow the binary evolution with that. We want to do that as a function of metallicity, because it may be a different type of formation process or different efficiency of binary formation in the distant universe than in the local universe. We want to provide or measure the binary fraction, the multiplicity fraction, triples, quadruples, whatever is relevant, and to provide for all those systems the distribution of orbital parameters. So as I said, I'm not going to do all that. I will focus on the mean sequence stars, mostly on O stars, and I will focus on the binary and multiplicity fraction, period, mass ratio, eccentricity distributions. All right, so this is a similar plot that Max Moo showed. If you want to cover the parameter space, you need to cover separation between a tenth of an AU and 10,000 AU. At a tenth of an AU, the 2 stars almost touch each other. And at about 10,000 AU, dynamical interaction in cluster will actually kill the binary very quickly. And also you have periods of the order of million years or more. So because massive stars live only a few million years, I like my binary to do at least an orbit to call that a binary. So if you want to cover this parameter space, you can only do that with a combination of different technique, with spectroscopy, with high-quality imaging, and in between using various kind of high-contrast imaging in which interferometry has played a prominent role in the last few years. And that's the great thing about ESO when you are a member state country, is that you get access to all those techniques for free as an astronomer. The country is paying, but I'm not. So I will do my talk in 2 bits. We'll first talk about the spectroscopic surveys, and then I will talk about the high-contrast imaging surveys. So let's start with spectroscopy. So I've been compiling the multiplicity survey, just doing spectroscopy over the last 5 years, and I come up with this ugly table. So I will have a more visual way to present this table in the next slide. I just want to draw the attention that, as I said, the fraction of, or the number of surveys focusing on the O stars is much larger than for the B stars, because the O stars are easier to observe. They are brighter, their radial velocity variation are larger because the masses are also larger, so you get better measurements. It's easier, and you can do that with smaller telescopes. So, because there's a lot of time, observing time, which is involved, if you can do that with a 1, 2, or 3 meter telescope, rather than to go to an 8 meter telescope, you of course have more opportunities to observe those stars. And the other thing I want to draw the attention to is in the number in the third column, which is the N, starts with 240. This is a sample size. So different surveys have had different sample size, and the sample size vary between about 50 to about 200, 250 stars. All right, so that is the observed fraction of spectroscopic binary. So it's basically the observed fraction of stars that show relatively large radial velocity variation and that we can use for follow-up to obtain their orbital solution. So the first one is our paper for 5 years ago, and then the size of the dots is actually the size of the sample size. The errors are smaller than the size of the symbol, but so our paper, which has only 70 objects, and then there's been a number of surveys by Rob Cheney, Sergio Simon Diaz, by Jesus Maïsa-Pelanis, and it's published in SOTA, Aldereta, the OWN survey, which I will talk a lot about later, that have been trying to observe every massive stars, every O stars in the galaxy, up to, well, not in the galaxy, every O stars within 3 to 4 kiloparsec. So this is, and then you have about 250 of those. So what you see is that aside from the paper of Cheney that has a little bit higher detected binary fraction, what you have is that most of the constraints are getting numbers between 50 and 60% of the detected binary fraction. Then you have the B stars. And then the B stars, there's only 2 surveys that have been doing B0 to B3 stars. Those are the stars that are 8 solar mass or more, and they got a binary fraction of 30 to 50%. And then only Rolf Cheney is doing the late B-type stars, and then the binary fraction is even lower. Now there's a problem there. You cannot take those values face on, because it's more difficult to detect binarity in a late B star than in an O star. So those observations need to be corrected for observational biases. I will come to that in a moment, but I want to add one more survey on that. So this is for the galaxy, and in the last few years we've been working in the Tarantula region with the VLT-Flam Tarantula survey. It was a large program with flames, which is led by Chris Evans, and we've been observing 800 O and B stars in the Tarantula region with different aims in mind. We wanted to do, of course, the multiplicity, also investigate the stellar rotation, investigate the properties of the starburst in general and the feedback of massive stars. And today I'm only going to talk about the properties of the multiplicity properties in that sample. All right, so those are the 2 results that we obtain. So we have an O star binary fraction, which is detected about 35%, and a B star binary fraction of the order of 25%. Again, keep in mind that this is LMC, so we are having more difficulties to detect multiplicity there than we do in the Carina region, for example. Okay, so that's the same table with just summarize 50 to 70% observed for the O stars, 30 to 50% observed for the B stars, the early B stars, and then 25 and 35% observed in the Large Magnetic Cloud, in the Tarantula region of the Large Magnetic Cloud. Unfortunately, very few observers have at this stage already corrected for the observational biases. So I cannot give you numbers for bias-corrected binary fraction, but for all those surveys. But the one that we have is our paper from 2012, where we obtained a bias-corrected fraction of 70% up to a period of about 8 years. And then there's the Cygnus OB2 region from Kobelnicki. Not the problem, but one of the differences you see is the bias-corrected fraction is lower than what we have. But they've done the correction for the entire sample that goes from B3 to O5. So they don't make the difference between the O stars and the B stars. And if you look at their observed multiplicity properties, which I think it's, no, screwed up. It's back. How do you get the, okay. The observed multiplicity properties was, oh, it's hidden. That's nice. The observed multiplicity properties were 50% for the O stars and only 30% for the B stars. When you do the average, you end up with something which is of the order of 55%. And in the LMC, we had 50% for the O stars and about 60% for the B stars, but with extremely large errors. So I think there's still a debate whether the binary fraction is homogeneous or whether there's some effect of the environment. I would say right now, binary evolution, given the star formation history of 30 Doradus, can explain the difference between those observations and those observations, but it would be nice to have other observations. All right. So that was about the binary fraction. So large number of spectroscopic binaries already, the order of 50 to 70%. I'll stick to those numbers. But that is not enough. What you want is, what is the number of stars that really interact? And for that, we not only want to know the ones that are in binaries, but we want to know the ones that are in binaries that are close enough to actually have something fun that happens during the evolution. And for that, you need the orbital distributions. So, I mean, you've seen those plots. That's our work from 2012, where we have the cumulative distribution of the period, observed, the crosses, and the mass ratio. And when we model our observational biases, the best distribution that reproduce our observation after bias correction is this dark blue power laws with an index of -5 and a flat distribution for the mass ratios. All right. So I want to say a few words about the strengths and the weaknesses of that study, because I'm probably the best person to criticize my own work. So among the strengths, it was a young sample, so we close to the initial conditions. We were volume complete, so we were looking at different clusters, and for every of those clusters, we managed to secure multi-epoch reservoir velocity measurements for over 90% of any O star in that cluster. 85% of the detected binaries have an orbit, so that we can correct and measure the actual the actual multiplicity orbital distributions. And then we had a self-consistent method in 4 dimensions to correct for the observational biases, the 4 dimensions being the multiplicity fraction, period, mass ratio, and eccentricity. Then, of course, we had a number of limitations. We had only 71 objects in our sample and only 40 binaries. And then if you look at the period eccentricity diagram, you see that there are regions where there's just no data points. And the question is whether, is this real or is this due to observational biases? And this is one of the reasons that prevented us at that time to investigate correlation between, for example, period and eccentricity. All right, so this is a comparison of a few works that follow up. There is the work by Kobelnicki in the Cygnus OB2 region that is on the left side. And they can fit their observation really well with a power law that is reasonably close within 1.5 sigma power law exponent. And then we did the same in the Tarantula survey, and then we get again a similar period distribution or best fit period distribution. For what it's worth, in this separation range or period range, the power law is actually sufficient to describe the data, because when you do a Kolmogorov-Smirnov test between your simulations and your observations, you get value of the order of 0.2 to 0.5. So there's no need to say that the power law is insufficient in that small separation range. So again, for the mass ratio distribution, both the signature B2 region and the galactic young open clusters actually agree really well with a flat distribution of mass ratio. So that was the state of the art up to 3 years ago. And then with my postdoc, Leonardo Almeida, we did a follow-up survey of the O-star binaries that had been detected in the 30 radius region. So we managed to follow 93 O-stars and obtain about 80 O-type orbits. And that was the largest binary survey of O-stars that was performed. And this is not in the galaxy, this is in the Magellan Cloud. So a different metallicity environment. So the great thing about having so many binaries is that you will also probe the rare and fun objects. I just want to highlight 2 of those objects because the people are here in the audience. We have VFTS352, which is one of the most massive overcontact binary, and we have evidence of chemically homogeneous evolution in there. So there's a poster by Michael Abdul-Massi, which is poster number 1, so that's easy to remember. So you can go and talk to Michael about it. And then we had R145. The masses are huge, 105 plus 90, so we have 200 solar mass in there is current masses, so not the initial masses. And again, we need chemically homogeneous evolution to try to explain the abundances. The winds are not sufficient. So if you have questions about that object, you can go and talk to Tomer, which I forget your name. I'm sorry, I forget to put it there. No, I forget to put it there. I know, Shenar. Apologize. So you've seen the guy is there, and he's not shy. All right, but one of the main scientific objectives was to get the period distribution for those objects. So we had our period distribution in red from the galactic open cluster. We had the Kopernikan distribution in blue, and then the Tarantula massive binary monitoring with 80 objects in the black. And you have to realize that there's as many objects in the black distribution than in the sum of the other 2 distributions. So based on this, this is observed, so it's not bias corrected, but there's no reason to claim that those distributions are statistically different. So again, that was the state of the art up to 6 months ago, but at a conference in New Zealand, Rodolfo Barba and his team came and they presented the result of the ARN survey, so it's the O-stars and WN star survey in the galaxy. They've been trying to monitor about 250 of those objects, and that is the period distribution, or the period histogram, that they obtain. And Rodolfo has been kind enough to send me that histogram, and I could build a cumulative distribution. That's what I'm going to show now. So that's the green. And you see that, again, there's a perfect agreement between this new super high-quality sample, so that's the new standard in the field, and what we did 5 years ago. So the conclusions most likely are still valid. There's one thing that we need to do now is to correct for the observational biases, but this is work in progress. So what we see is that there's not too many variation between different environments, the galaxy and the 30 radius region in the LMC. When different metallicity, I know there's not a huge metallicity difference, but it's the first indication that, at least in that small range of metallicity, nothing dramatic is changing. And then I've only shown the period distribution, but if you look at the mass ratio and eccentricity distribution, there's no indication that they should be different as well. So what we find is a relative universality on the binary properties, and to me, this is indicating that those binary properties are set during the formation process. And this, again, is in line with some of the suggestions by Max Moo at the first talk of this meeting. And then I want to emphasize that on poster 69, Oscar Ramirez Agudelo and collaborators are now working on the B-stars in the Tarantula region, and they will, in the next year, the next 2 years, because it's a lot of work, provide the same kind of reference sample for the B-stars. Okay. So let's go back to the periodic eccentricity diagram. And I want to show you the 2 results from the ARN survey that supersede our sample, and then from the Tarantula massive binary monitoring. All right, so that was the uncertainty whether there were or not data there, and this is what Rodolfo Barba is obtaining. So even at large period, the eccentricity diagram is fully populated. So to me, this is pointing or indicating against a thermal distribution of eccentricity. And then that is the 30 radius results, and again, we have the same similar distribution. I'm convinced that this is an observational biases, and I'm currently busy trying to model that, but it doesn't matter because up to periods of 3-4 years, we see a range of eccentricities that's just not following a thermal distribution. So that is two important results, a high binary fraction, similarities of the period distribution and the other distribution, a different environment, and then a period eccentricity diagram which is well populated everywhere up to a period of at least 3 or 4 years. I had the intention now to talk about something different, that was the rotation rates, but Norbert has simplified my life and actually already presented those results. So because two people is trying to present the same results, I think show the importance of those results. So those are, Norbert has been talking about the data from the Tarantula region, but I want to point Sergio Simon Diaz that obtained similar results in the Milky Way, where for single stars you have a peak of short period of low velocity, low rotational velocities and a tail, and you find that in the LMC and you find that in the Milky Way, and we were suggesting that this is coming from binary interaction. So I'm going to skip over this. Have more time for questions, but then I will repeat the conclusions that all stars may be born as slow moderate rotator, so no fast rotator or no rotation faster than 150 or 200 kilometers per second, and that rotation only becomes important after binary interaction. All right, so let's now move to the other was I inverted? So the other, or the longer separation range, and that you cannot do with spectroscopy, because radial velocity variation just become too small to be detectable, even with high quality data. So interferometry and other techniques like space aperture masking, adaptive optic, and the Hubble Space Telescope become there very useful. And the status 20 years ago was that we had a lot of spectroscopic binaries, which is the gray histogram there, and a lot of visual binaries, but in between we had very few there. Very few objects that were detected, and that was called by Mason to be the interferometric desert, the interferometric gap, because there were no technique actually allowing people to measure or detect binaries in that range, except for interferometry, but 20 years ago interferometry was very inefficient, so it was not possible to get a large sample. So now what I want to present is the results of an ESO large program. It's only been possible thanks to the effort of the people at the VLTI to make the VLTI a super efficient machine or machinery to detect binaries. So we have been combining long baseline interferometry and aperture masking and adaptive optic, and we had about 170 targets. We detected almost, well over 200 companions, but 200 completely new companions that were undetected before. And on that plot, I will also show the results of Aldereta, where she has been using the HST fine guidance sensor, and that is her sensitivity detection regime. All right. So that was the companions that were known to our sample stars before our survey. And if I add those, you see that suddenly the interferometric gap, which was here, is now completely filled. So there's a lot of binaries that had been completely missed. Adding the HST results confirm that it seems to be a nicely continuous distribution. And if you compile all those data, also taking into account the spectroscopic binaries, you now reach multiplicity fraction, so the number of central stars that have at least one companion of over 90%. And those companions, the first one is always found to be less than 1,000 AU apart. The average number of companions, at least 2 companions per star, but there are stars that have 4 or 5 companions, and stars that have only 1 companion. And then if you limit at the dwarf in our sample, we reach a detection fraction of 100% within 100 AU, and we have 2.2 companions for the unevolved all stars in our sample. So this is magnitude, and this is angular separation. And what you would like to have is mass ratio and physical separation, and that's been the work of Frank Tramper, which is now in Madrid. So it's the same observation. It is mass ratio, and given the magnitude difference, we can go to mass ratio of 0.2 or lower with NACO, and we go from separation from 1 AU to about 10,000 AU. So notice here that this region of the parameter space, the triangle there, is empty. So that is in line with the results of Max Mood that at some point there is correlation between quantity like the mass ratio and the separation, and you cannot use uncorrelated relation if you want to model an entire population of binaries over the entire possible parameter space. Okay. Can we see this? Yes, it's okay. So this is the cumulative distribution of the number of companions as a function of the separation in milliarcsecond. Below this regime is spectroscopic binaries. We already have 50 to 60% of spectroscopic binaries, and then we reach 100% at about 30 milliarcsecond, which given our sample corresponds to 100 AU. But now, interestingly, you have triples. You have at least 25 to 35% of detected triples without any bias correction. And then you have about 10% of quadruple and a few percent of quintuple objects. So what we're now busy doing is to go beyond SMASH, and Sphere is opening a new window in the parameter space, and that my PhD student, Alan Reno, which couldn't be here this week, but he will be in Nice next week for the people that go there, and he will talk about those results, is analyzing a sample of 40 stars that have been taken in order to see whether we have companions in there. This is the early days of the analysis process, but I only want to flash one result, which is on QZ-CAR. So QZ-CAR was observed in the SMASH survey, and we had detected 1, 2, and 3 companions that are here, here, and there on the brightness, contrast, angular separation diagram. But with Sphere data, you find this new companion. So this window is 1.7 by 1.7 arcsecond. So we immediately find something which looks extremely bright. And when you compute the magnitude contrast of that companion, you find that despite it appearing extremely bright in terms of number of counts on your detector, the magnitude contrast is 6 magnitude, only in 25 minutes of observing time. So Sphere will allow us to see whether or not there are companions in there. So we now have been analyzing more samples, and this is detection maps of all those stars with Sphere, and you see that many objects have companions here, here, here. But we're not sure yet whether we find extremely faint companions. So we are, or Alan is working on that for his PhD project. So next year, I'm sure we will have more results, and we can exclude the presence or not of companions, of extremely faint companions. And the last thing I want to flash, and that's for people interested in triple systems, is that we have been doing a good job as a community to obtain large samples of orbital period and orbital solution distribution for the spectroscopic regime. But what happens at larger distances? Because in there, this is where you start to find the triple companion or the third companion of triple systems. So we've been doing a long-term VLTI follow-up, and that has been going on for 7 years. So thanks to everyone that has been in the OPC to give us time one period after one period after one period, and also thanks to people that thought about doing monitoring programs, because then we only have to submit a proposal once every 4 periods. So those are examples of binaries that for which we managed to measure the orbit, and we have a large diversity of a circular orbit with a separation of 1 milliarcsecond only, so this is a few months period, up to eccentricities of 0.99 and a period of 150 years. So we have only 11 orbits so far, but we're still following up another 30 objects. Interferometry is beating spectroscopy for those long period systems in getting you extremely accurate period and eccentricity, so we'll be able to populate the period eccentricity diagram to a larger separation. And for stars in the spectroscopic regime, we can get this 3-dimensional orbit, so we'll get absolute masses with precision of the order of 5%. And then we will get orbital inclination. That's what interferometry is giving you. So at some point, we'll be able to tell something about the mutual inclination of the inner binaries and outer binaries in triple systems. That will be an important constraint for people studying the lead-of-causi mechanism. All right, I still have 18 seconds, according to my record. So there's been a lot of progress in the last 5 years. There's a number of surveys from spectroscopy in the Milky Way and the Magellan Cloud at high resolution in the Milky Way. We've crossed the interferometric bridge. We have even higher multiplicity fraction, getting close to 100%. A lot of companions, so we have know that the average number of companions is over 2. And then we have similar properties across a different environment. And as a last slide, and just was to let there, what I think are the next things that we could achieve in the next 5 years is to actually get the physical properties of samples of 100 binary components and place them in an exponential diagram as we did for the single stars. So that would be interesting. We can investigate the extreme brightness ratios. We can check whether the properties of the B stars that are dominating the supernovae, actually in terms of number, is actually the same as the one for the O stars. We can try to look at the multiplicity properties at higher masses, at evolved stages, like the Wolf-Rayet stars, and in relation to other talks this morning, we are, in the next 5 years, going to identify and characterize, I believe, a significant number of post-interaction products, and that will provide constraints to the outcome of binary interaction. Thank you very much, and if you have any questions,